Hello. Last time I discussed with you the Work-Energy Theorem, which basically states that if you have a system and you drive the system by using a force F from point A to B, then the work that's done on the system is simply given by the change in the kinetic energy, the initial kinetic energy minus the final kinetic energy. Well, this is a very interesting result because the work that's done on the system is the change of the kinetic energy, meaning that you only care about the kinetic energy of the system in the beginning and the kinetic energy of the system in the end, and you don't care about what happened in between. Which makes you think that perhaps you can also formulate the work in this way. So the question I have in mind right now is that can I have a work that's like similar to the kinetic energy case? Can I have a work that's independent of the details of the system? Can the work be given in terms of what happens in the beginning of this and what happens in the end? So that's the question I have in mind today, and this is what I'm going to try to answer. And once I have the answer for this question, I'll try to investigate interesting physical systems depending on what kind of result I get. So let us start by investigating the Work-Energy Theorem again. The Work-Energy Theorem simply tells me that the work that one has to do to take a system from point A to point B by means of a force F, which is just simply the change of kinetic energy, where Vb is the velocity of the system at point B, and Va is the velocity at point A. So this is the difference in kinetic energies. Now, this side of the equation is just the change in the kinetic energies, which just depends on the final kinetic energy and the initial kinetic energy and doesn't care about what happened in between. But this side, well, I have an integral a to b f dot dl, or let's for simplicity consider just a one-dimensional case, which is to say I have f dx from a to b, is formulated in this way. And the question I have in mind, whether this integral can also be given independent of the details of the system. So just the initial configuration and the final configuration. And if F, the force, can be given as du over dx, where u is just some scalar function, depends on the position only. And if I plug it in here, then what I find is that this integral turns into the integral from a to b du over dx times dx, and dx cancel out, and I get ua minus ub. So the statement that I find is the following. If force can be described by a derivative of a function, of a scalar function, then this integral, which tells me what the work that's done on the system is just given by the values, the initial and the final values of this scalar quantity. This scalar quantity is called a potential energy. And then this equation basically states that if you have a force that is derived from a potential energy, that's a derivative of potential energy, then the work that's done on the system by using this force doesn't depend on the details of the system. It just takes the values, the potential energy at A minus the potential energy at B. So you just derive a system by using a force that can be derived from a potential, in which case the work that's done on the system doesn't depend on the details of the system, just the initial configuration and the final configuration. So what is so special about this definition? Well, let's take a look. So in this case, I can just write down the UA minus UB is equal to a half mVb square minus a half mVa square, which basically tells me that if I take this equation, this UB here, and 1/2 mVa square over there, what I get is 1/2 mVa square plus UA is a half mVb square plus UB. So this is very interesting because it tells you that if a system is driven by a force that can be derived from a potential energy, which is my scalar function over here, then the initial configuration here, I have 1/2 mv squared, which is the kinetic energy of the system, plus UA, which is the potential energy of the system, is equal to the final potential energy plus the kinetic energy, which I name as the mechanical energy. So I say that the E the mechanical energy of the system is given by the kinetic energy plus the potential energy, and this quantity, the mechanical energy of the system, is conserved if my force F is caused by a potential energy. Now, since I have this definition, then I can define the potential energy of the system at a point A. So I just simply integrate this. I take the dx to the other side and I integrate this. And this is to say this is from an origin to A, F dot dl. So I can define the potential energy at a given point. And you may say that, well, you have an origin here. So I just define the potential energy with respect to some origin. And you may wonder where this origin is. That's a funny thing here. And it looks like the potential energy depends on the origin. And that's true, that you define the potential energy at a point depending on the origin. But what you measure as a work is the potential difference, not the potential energy. So if I calculate the potential difference, well, that's simply minus to A F dot dl plus O to B F dot dl. So although I have defined everything depending on an origin, now I just change the boundaries of this integral, which flips the sign, so I get from A to an origin F dot dl plus the origin to B F dot dl, which simply tells me that the change of potential energy, which is the potential difference, doesn't care about the origin. It just tells me that independent of the origin, wherever it is, your result is just the work done on the system. So you can freely choose your origin. Just whatever is easy to you, you can just make that choice and investigate your problem. Let's now think about a couple of examples such that the force that derives the system is caused by a potential energy difference. Now, one example could be gravity, because if I have the baseball like this here, the force acting on this baseball is clearly m times g in minus y direction, so I assume that this is my plus y direction, which tells me that I can derive this force from a potential energy that is given by mg times y. So if I take the derivative of this potential energy with respect to y, I get mg, I put the minus sign by definition, and I get minus mg, which tells me that the force that's applied by gravity is in the minus y direction. Another example that you can think of is the mass and the spring system. So in the spring and the mass system, you have the force that's acting on the mass is minus k times x, and this force can simply be obtained by the following potential energy, kx squared. You can see this simply by, if you take the derivative with respect to x, you got k times x, you put the minus by definition, and that tells you then the force acting on the mass in the spring and the mass system is minus k times x. Now, as you see, this doesn't care about the details of the system. It just asks you where you started, what's the potential energy, what's the kinetic energy, and where you end. What's the potential energy in the end, and what's the kinetic energy in the end. To make my point clear, let's think about the following example. So I'll think about the roller coaster motion. Okay, so what I'm going to do right now is that I have an object here, and I let go of the object at this height. So let's say this is h, and this is the ground. So I let go of the baseball at this point, all right? And what I'm having in mind that whether this object, let's say this is a baseball, can just go through this loop and continue in this direction. So if I look at the conservation of the energy, let me call this point A, and let this point be B, and let's say the radius of the loop is just R. Then the conservation of energy tells me that, well, I just let go of the baseball, so it doesn't have an initial kinetic energy, just the potential energy, which is mg times h. And when it gets to here, I say that, oh, okay, it has a potential energy, let me call this mvb squared, and the kinetic and the potential energy, which is mg times 2r, which is the height here. Well, this doesn't tell you much, right? It just tells you that, well, you started here and you get to that point. It doesn't tell you whether just you go through this loop, or perhaps you just follow this path, right? Why not? Because if you also follow this path, you got the same equation. So as I mentioned, this energy or conserved quantities, they don't understand from the details of the system. They only care about how you started and how you ended. Here, this is how I started and how I ended. I might have followed this path or that one. This equation doesn't care about it. Okay? So which equation cares about it? Well, for me to make this point, my central acceleration should be greater than the gravitational acceleration, which tells me that VB squared divided by R must be greater or equal to G. Now this is about the details of the system. So you can never ever solve the problem whether this baseball can make it to here by using just the energy equation. So we have to consult to this equation, which concerns the details of the system. So if I solve VB squared from here, where m's cancel out, I got 2gh minus 4gr equal to VB squared. And if I plug it back in here, what I get is 2h minus 4r is greater or equal than r, which simply tells me that h must be greater or equal than 5 over 2r. So if I let go of the baseball from a height that's greater or equal than 5 over 2r, then my baseball will just go through this loop and continue its motion. So we have now seen that if I have a force that's caused by a difference in the potential energy, then the work that's done on the system by this force is just path independent. It's just given by the difference of the potential energies. And you can define a quantity called the mechanical energy, which is just the sum of potential energy and the kinetic energy. And this quantity is just constant. There's another way to see it. Now, I would like this quantity to be constant, which means that dE divided by dt must be 0. And let's just take the time derivative. So the time derivative of this quantity is just mv times dv over dt plus the derivative of this quantity with respect to time, but this is implicitly depending on time, so I just use the chain rule. I get du over dx and then dx over dt. Well, dx over dt is nothing but just the velocity, and dv over dt is nothing but the acceleration, and m times a is just nothing but the force, so I get f plus du over dx. And as promised, if f is given by minus du over dx, then, as claimed, dE over dt is constant. It is conserved. It doesn't change over time. And I call such a force a conservative force. So a conservative force is the force that's caused by the change of the difference in potential energy, and conservative force is a force that derives the system, and the work that's done by this force is just path independent. So what? I have this, and what am I going to do with this? Well, this has the following advantage. You may think that, I have Newton's equations, so I can solve Newton's equations. Why do I need to bother this? Well, Newton's equations are second order in time derivative, you remember. But this equation is first order in time derivative, so it gives you a huge, tremendous advantage. This is just simply dx divided by dt squared plus u of x. So let me take this to the other side, all right? And let me multiply the whole equation with 2 divided by m. So what I get, 2 divided by m e minus u of x is equal to dx divided by dt squared. So let me take the square root of this equation. So I get this. And I take this one to here and that one to here, because this is a constant, that's a constant, and this only depends on x. So what I get is dt is plus and minus dx square root of 2 over m e minus u of x. And I can integrate this. And I integrate it, and what I get is t minus t0, some integration constant is plus and minus dx divided by 2 over m e minus u of x. So we solve the system. Once you give me what your u of x is, I can integrate this, and once I integrate this, I know how x depends on t, and by starting how x depends on t, I can figure out what the positions are, accelerations are, velocities are. So the entire system is solved, and that can be achieved because I have a system that's only first order in time derivative, not the second order like the Newton's equations, thanks to the conservation of the mechanical energy. Another great advantage of having a constant like the energy is that you can understand the systems without just thinking too much about its details. For instance, let's just take a look at the, this is my potential energy, and this is x. Let's think about the spring and the mass system, in which case u of x is simply given by half k x squared. In this case, I have something like this. Okay, so this is my u of x, which tells me the following. Suppose that I let go of my mass at this location. Let's say this is some x0, okay? So I'll let go of the mass at this location. So I let it go so it doesn't have a kinetic energy, just a potential energy. Now what I know is that right now, here, there is a force acting on the system, and it pulls the mass to the equilibrium position, and this is the equilibrium position. Here, the force acting on the system is just 0. So my mass just moves to this position, and as it moves to this position, the potential energy gets lower, which means that the kinetic energy of the system increases. Now, as I get here, the potential energy becomes 0, which means that the kinetic energy becomes maximum. So my mass has a kinetic energy, and it's moving towards this direction. What I know is that the energy of the system is constant, which means that the mass that I release here can make it up here, but it cannot exceed here, because if it exceeds here, then the potential energy becomes more than the potential energy that I give, which defines an imaginary velocity, which is not possible, not physical. So I know that if I let go of the mass here, it will just oscillate between these 2 points. It's x0 and minus x0. Well, that's simple to understand because this is a very simple system. Well, let's think about a bit more complicated system. For instance, let's think about this potential energy. Let's say I have mx cubed minus 3x. Well, you may say that, okay, let me plug it in here and then solve this integral, then I'm done. Yes, you're done, but the solution that you are going to get is going to be given in terms of elliptic functions, and I don't think you are very familiar with elliptic functions. Nevertheless, it's easier to understand this system just by drawing this diagram, the potential energy diagram. So this has 3 zeros. One is at x equal to 0, the other is at x equal to minus square root of 3 and plus square root of 3. And it has 2 extremas. One, so I know that the force is 0 at 2 points, which is just 3m x squared minus 1. So at x equal to plus and minus 1, this one, the system is at equilibrium. There is no net force acting on the system, because if x equal to plus or minus 1, du over dx, thereby the force is 0. So I have a system something like this, where this happens to be 2m. And this point is plus 2. Now I know that this is my diagram for the potential energy. And now I don't have to think about the details of the system, because I can just look at this diagram and I can say, well, if I have a mass, if I have an object, and I put my object right here, okay, some point that's less than, some x that's less than plus 2, and also, let's say this is minus 1, so this is like minus 1. So if I do that, what happens is that, well, if I put my mass here, put my object here, I know that it has a potential energy here, and it doesn't have a kinetic energy. I just let it go. So what's going to happen is simple. It's very similar to this harmonic oscillation. It will start oscillating between these 2 points. If I let it go at this point, it will start oscillating between these 2 points. If I let it go at this point, it will start oscillating between these 2 points. But if I let it go at this point, for instance, then the potential energy of the system is larger than this point here, the top of this hill. So if I let go of this mass, well, it will just pass through this top of the hill and it will accelerate forever. These 2 points are special because at these 2 points, the force acting on the system is 0. So if I take this object and put it here, then this object will stay there, okay? Because the force acting on the object is 0. Or if I take my object and put it here, then it will stay there because the force acting on the system is just simply 0 there. So these are equilibrium points, okay? But these 2 points are not the same. They're a bit different from each other. The reason is that because if I just take this baseball, let's say this is a baseball, and I just take it away from the equilibrium point, okay? If I do it for this point, it will start oscillating. These 2 equilibrium points are different than each other. I call this equilibrium point as a stable point. The reason being is the following. If I take the mass and take it away from this point, then it will start oscillating around this equilibrium. So the force will try to attract this, no matter what, to this equilibrium state. This is called a stable point. However, for this one, if I just take the mass and put it right here, then it will just start accelerating towards this direction. So this is an unstable point. So today I discussed with you the work-energy theorem in the presence of a force that's derived from a potential energy difference. And what we noticed was that if there is a force that's driven by a potential energy difference, then we can define a conserved quantity that we call mechanical energy. And in this case, the system becomes independent of the details of the system. You can understand the system by just looking at what happened in the beginning and what happened in the end as such. This gives us a tremendous advantage such that I can define the system that I have by just using a first order differential equation rather than the Newton's equations, which are second order in time derivative. Furthermore, I found a way to understand the system without looking at the details of the system. This is a property of the conserved quantities, and I think from this day forth you will hear more about them, such as the conservation of the momentum and conservation of the angular momentum. So these are the conserved quantities of the Newtonian mechanics: the energy, the angular momentum, and the linear momentum. So I wish you good luck with your studies.